Hi guys, can I get a sound check?
I can hear you.
Great, thanks.
Sure.
All right. Hmm. Shoot. Shoot. Oh, no. Sorry guys, I'm having a little bit of a technical difficulty. Just give me a second, please.
That's okay.
Hmm. Sign in. Okay, thanks guys. Let's see. All right, so let's get started here. What is it, 21st? 20. So let's do I guess a quick review. I think the key things I wanted you to take away were, again, there's these three diode models. Three diode models. And so, two of the three are for ease of analysis. Okay, so there's the real diode model, which is if you have a circuit where you're putting a voltage across a diode and looking at the current, you get this exponential behavior. And this curve is, the I sub D is I sub S exponential of V sub D over V sub T minus 1. Okay, where V sub T is KT over Q and that's equal to 26 millivolts at room temperature, or 300 Kelvin. Okay, and so here, this equation looks like an exponential because this exponential of VD over VT here gets to be much larger than 1, so I sub D here is approximately I sub S exponential of VD over VT. Okay, and here, so this path is exponential of VD over VT is much greater than 1, so that term goes away. And this path is the same exponential. VD over VT is much smaller than 1. And all of this is happening because VT is only 26 millivolts. So as soon as you go to plus or minus a few hundred millivolts and you have this exponential, even a few tens of millivolts really, this exponential kicks off and you're either much greater than 1 or much less than 1. And then here, so you end up with I just minus I sub S. So that's sort of the simple equation there. So this is the, what we call the exponential model. Okay, number 2 was, we said for ease of use, let's approximate that into like a switch that either is on or off. And then when it's on, it's a dead short. When it's off, it's a complete open. So in either case, so we have the, so simple models. And the whole point of these 2 models that we're about to talk about was just so that it's easy to analyze complicated circuits. Okay, so the simple model is that if
do you mind scrolling up real quick?
I'm sorry?
Do you mind scrolling up for me real quick, please?
Oh, sure.
Perfect, thank you.
Sure. Let's hear a review. Oh, so the first one we call the ideal model. And the second one we call the constant voltage model. So again, I can't emphasize this enough. There's nothing like scientific about these models. They're just meant to make life easy to analyze a circuit relatively quickly, certainly quicker than having an exponential thing. Anyway, so the ideal model, again, what we said was instead of this exponential characteristics, what we say is either if I was going to draw the same V sub D versus I sub D curve, again, this is a voltage source across the diode. It would turn on as soon as V sub D went positive, it would turn on with 0 resistance. And over here, R sub, what do we call it? R sub D is equal to 0. And notice that I always have to write this V equal to IR. So I is V over R. And if R, so if R is equal to 0, then V is, I is V over 0 is, goes to infinity. As soon as V just gets a little bit positive, I just pegs, okay? And then so it would look like this, and from a circuit perspective, it looks like a switch that's closed. So it looked like this circuit, if I redraw the circuit, it just looks like V sub D as just shorting across itself, okay? So that's on this side. On this side, we just say the simplified model is the switch is just off, and here R sub D is infinite. And again, I is V over R, so it's V over an infinite thing, and that's equal to 0. And that is as if we had V sub D just doing its thing in space. We just open the switch. Okay. Any questions about that, guys? And again, the idea is that we're just trying to approximate. We're trying to make life easier and just saying, hey, like this thing is like the green thing, which is our real characteristic, is the same as this red thing. Okay. Which is our ideal model. And then we had the constant bias model, constant voltage model. And that was basically taking the same characteristics and saying, well, it'd be cool if we have this green thing that we're trying to model. Let's move over where the diode turns on to a place called VD on. And that's really the only difference between the ideal diode model and the constant voltage model. It's trying to make it a little bit closer to what you'd see. And here, what you'd end up with is, again, I is, again, infinite, but if VD is greater than VD on, okay, so it'd be from here on out, not over here. And so it would look like we've got a voltage source driving another voltage source or driving a battery with a voltage of VD on. Okay, which is basically, if you actually do that in the lab, they're just gonna, well, don't do it in the lab, but they would just sort of just peg each other. They'd both start sourcing current and one of them would win. But anyway, for this discussion, basically, you just end up sourcing as much current, an infinite amount of current into this VD on, because again, this guy is able to apply an infinite amount of current. And then if in this range, so if V sub D is less than VD on, then again, I is 0. And so by the way, this should be greater than or equal to VD on. And same here, if it's, this is if V sub D is greater than or equal to 0. Has that equal to? Less than, I is 0. And then again, you would end up with an open switch with a battery. But the battery doesn't matter there because it's an open circuit here. Okay, so that was the sum total of the main thing. And then we did a bunch of examples to try to see how useful this is in the sense that it was making our life. Hopefully what it showed was using these ideal models was making our life easy in analyzing circuits. And I know at this point, to sort of preserve our sanity, all the examples in the book are fairly simple. So you'd go, well, do I really need these models? Push comes to shove, I could still solve iteratively like we did a few times. But the idea is that these are really, really simple examples, and any kind of a useful circuit, you will have like a bunch of diodes, you'll have a bunch of other active elements, and you'll quickly run into trouble if you didn't simplify things. Let's see, do I want to say anything else here? I think that's pretty much it for what, this is sort of the first simplification approach, okay? And this tells you basically if a diode is on or off. That's what, in a circuit, with respect to the voltage, okay? So that was what we had before. And now we're introducing another approach, another simplification approach. And that's called the, and that's what all we're going to talk about today is called the small signal model. Okay. So what does that mean? This thing always confused me, even until like I never understood the concept of small signal, certainly in undergrad. I think at some point in grad school, I like started to like sink in. So here's the idea. Okay, so we simplified using these switches, and this is another type of simplification. And I'm gonna give you guys the punchline, and then we're gonna go and derive it and do a few examples and stuff. So this is the idea. You have the same exponential behavior. Okay, so we have this guy. Yeah. So, sorry. Let me go back to this one more time. Sorry, I forgot to mention one thing. I remember. So, so what when you get a problem, or when you're doing a design, but let's say for the sake of discussion, let's worry about this class first. When you get a problem, what your approach should be first you see if the problem specifies using an ideal model or a constant voltage model to try to solve the problem. Okay, if you don't see either one of those, it's kind of a hint that you might have to use this exponential model. Sometimes you have to use the exponential model. For example, if you have, we looked at a case where you had two diodes in parallel, and if the diode areas weren't the same, or the diode I sub S sort of currents, remember we have this I sub S here, which is a very important number. And it's a given thing, so it's I don't know if it's called like reverse bias current, but let's call it. Remember, this would be given to you guys, or either in the problem or given to you in a spec sheet if you're really using a diode to design with. And it's something like, I don't know, it's a pretty small number, but it ends up making, I don't know, it could be anything, but it's a pretty small number in terms of amps, but it makes a big difference in this sort of the voltage versus diode characteristics, voltage versus current characteristics, because of this exponential behavior. So anyway, so besides having the models, you're going to also, by doing the problems, the homework problems, etc., you sort of figure out when to use which model. Okay, and then sometimes you have to use the exponential model. Okay, sorry, sorry to digress, but I just wanted to say that about those two models. So the small signal model, again, is a simplification approach. And again, let's say you had this exponential behavior. What you try to do now, though, is to say, hey, if let's say I've already calculated my current, for the sake of discussions, at some I sub 0. Okay, let's say I already calculate that. And I know what I sub 0 is. If I get a change in V sub D that's small, and this is where the small signal comes from, if this change is very, very small, okay, and I sort of look at just this part of the circuit, so let's say I had something like this, and I'm just looking at sort of, let's say this is a zoomed in version of this, and I'm just looking at, this was I sub 0, and this is I sub 0 prime, let's say, okay? and this was V sub 0, and this is V sub 0 prime. Okay, so I'm just zoomed in here. Basically, the idea here is that if this delta V, if delta V is small, then I can pretend like this curve is just a straight line as opposed to an exponential. So I can pretend like I just have a resistor between I sub 0 and I sub 0 prime and quickly come up with a new numbers either for V sub prime, 0 prime, or I sub 0 prime. So basically you're saying if I keep the change in voltage, if my input signal is a small signal, then I can get a linear approximation to my circuit. Okay, so that's the idea behind this. So now let's look at why this might be useful. Let's say, so I'm not gonna do example. Any questions about that? I know I'm just sort of giving you guys the headline here, but it's sort of a very simple concept, but it can get confusing. And let me add one more thing, sorry. So if you're looking at this overall picture, what you're saying is, if I have a diode, I'm gonna look at the circuit in two different ways. And I can do a superposition of both of those together to get the answer, okay? In the one case, I just look at it as like the actual diode with some VD on. Okay, so this is in large signal model. So it's a combination of this large signal model with a VD on, and I go about calculating V0, I0, and those kind of things, okay? And and also a small signal model, which is would be just like a resistor. And it'll have a series resistance R sub D, and we'll figure out how to do that. So it's basically a superimposition of these two, and this ends up being extremely useful when your circuits get complicated. Okay, so let's use an example of a case when something like this may be useful, but let's first look at why not having it might be a little annoying. So here's an example from the book. Example 3.7. Yeah.
So, sorry to interrupt you, but just a quick question.
Mm-hmm.
The large signal model, that's the exponential nonlinear model, right?
That's the exponential nonlinear model. So that's what you would use to calculate the VD on, for example. But you'd only calculate it at like one point. So if you have, say, a sinusoidal input in, you'd calculate at one point in that sinusoid, and the rest of the signal, you just assume it's a small excursion. And I'll just give you guys an example so you'll see exactly why it's useful.
Thank you.
Sure. Okay, so example 3.17 says, what was this? The story was that, story in the book is that, you need a 2.4 volt charger for your cell phone. You've lost it, and there's none to be found. You go and buy a voltage regulator that is a 3 volt voltage regulator. Okay, or adapter, sorry. So you need a 2.4 volt adapter, but you can only find a 3 volt adapter. So the problem is you have your adapter, it's hooked up to the wall, and it's pumping out 3 volts, but you need your cell phone it needs 2.4 volts. So what do you with that? What do you do with that? So, and the idea is that what you do is, let me actually draw the 2.4. Let's say 2.4 volts needs to come in. No, sorry, it's okay. So what you do is you've decided that, well, I think, you know, when we talked in the class, we said that the VD on is, you know, more or less 0.8 volts, you know, 0.8 volts, 0.7 volts. We said that that VD on isn't going to change much more than that. Oops, sorry. So we have this device. So if we have a forward bias diode, the voltage across it is going to be around 0.8 volts. Okay, we talked about that in class. So what if so I needed 2.4 volts. So what if I stack 3 of those 0.8 volt guys? So all 3 of them forward biased. So each one has 0.8 volts across it. And that gets me my gets me my 2.4 volts. But then I also need to get a current I need a current for these guys to be on. Let's call that I sub X, and I need to generate that. Plus, you know, I need to go from 3 volts to 2.4 volts. So what I'm going to do is I'm just going to drop a resistor here, say 100 ohm resistor there, and basically have this guy take up this difference. So this resistor will have 3 volts here, 2.4 volts here, and I'm using 3 forward bias diodes. Does that make sense to everybody? Why that might make sense, sort of as a first level approximation? Again, you just have, we said, each one of these diodes in the constant voltage model, each one of them just looks like a battery of VD on, and a VD on we said is typically 0.8 volts. So you stack 3 of them up, it's like sort of like having 3 0.8 volt batteries in series. And then that gets you to 2.4 volts, but then you also actually have to actually drop that voltage to put the resistor on. So hopefully that makes sense to everybody. Does it seem like, does anybody have a question why it wouldn't make sense to do something like this? At least the first order? No? Okay, cool. So the question becomes, I think the first question is, let's say you needed to do this. Now we said VD on is approximately 0.8 volts, but precisely it's VD on, say, is precisely, then let's say this is all happening in the lab, so it's room temperature. So it's V sub T natural log of Ix over I sub S. Okay, because we're doing this in the lab, this is equal to 26 millivolts. So, you know, we said it's, approximately 0.8 volts, but that really depends on, this I sub S, right? Exactly what it is. Maybe it's 700 millivolts, or maybe 850 millivolts, depends on I sub S. So the first problem is, let's say we're going to go buy these diodes or go get them from the lab or something. What I sub S, if you could have any I sub S, what I sub S would you need? This is kind of a little bit backwards, but anyway, you guys will we'll see how this works out. So the first thing you do is you say, okay, well, I need 2.4 volts here, right? And I have 3 volts. So I put a 100 ohm resistor across from one point to the other, and that has a 600 millivolt drop across it. So first thing I want to do is calculate I sub x. I need to get this guy in the numerator of the natural log. So I sub x is just equal to 3 volts minus to 2.4 volts. We said we're going to use a 100 ohm resistor, so that ends up being 6 milliamps. Okay, for I sub s. So then the other equation, so these equations you guys should like remember is just enormously helpful. So V sub D is, I'm just going to rewrite this guy. V sub D is V sub T natural log of I sub D over I sub S. And then the other way to write the same thing is or I sub D in terms of I sub D and I sub S is exponential of V sub D over V sub T. So these are the equations for V sub D and I sub D, assuming the diode is in forward biased. Okay, so now we have this I sub x. So we want to figure out what I sub s we'd need for this. So what I sub s would we need? So we have I sub x. So I'm going to use this equation. So 6 milliamps is equal to I sub s, which is what we want to find out, exponential of, we know we'd like V sub D to be 800 millivolts. And we have V sub T, which is around 26 millivolts. Then I'm going to reorganize all this stuff and get I sub s is, what is it, 2.6 times 10 to the minus 16, something like that. So assuming you had this a diode with this I sub s characteristic, if you put in 6 milliamps of current through this diode, you would have exactly a 0.8 volt VD on, and you put 3 of them in series and you get 2.4 volts. So you're good. Any questions about that? Okay, so far so good. Let's say you did that. Now the second question is, assume for a second that this voltage, the adapter voltage, increases to 3.1. Okay, so you already have this circuit, you already have these diodes. I don't know why the adapter would go to 3.1, but you know, there's variation in voltages. Maybe there's a, you know, power shortage and the line voltage drops from 110 volts to 100 volts, and then, or vice versa, and you end up with 3.1 volt. And you already have all your diodes and circuits. So the question is, what happens? What does your cell phone get? Okay. Before at 3 volts, the cell phone was getting 2.4 volts. Now we want to know if there was just a small change from 3 volts to 3.1, what happens? Okay. So the first thing we do is we make, so again, so we have the adapter. This guy went from 3 volts to 3.1 volts. We had a 100 ohm resistor and we had 3 diodes. And we had the cell phone. Now, so the question is, what's this voltage? Now, the tricky part is that as the voltage changes, this current I sub x is going to change, and that change in current is going to change the VD ons, which then change the current. So does that make sense? So, you know, you have to assume the current goes to something, get the new VD ons, and then see if that VD ons will affect the current. Okay, because this guy is not going to stay at 2.4 volts. The question is, what does it go to? So as soon as this guy changes, it changes the I sub x, which changes the VD ons. And this is why this is a, you know, can get to be a complicated problem. So the first thing you do is you say, well, I've got this characteristic, okay, that if my, even if my current changes quite a bit, so I'm out here, so I was on VD on of 0.8 volts. Even if my current changes a lot, this VD on doesn't change a whole lot. So let's just start by assuming that the current, like all this whole 0.1 volts goes across this resistor. So we're going to assume to begin with that there's very little change to VD on, and then we're going to plug that number back in to the equation and see if, you know, so a sort of iterative procedure. Okay, so let's, for the sake of, so iteration 1, assume VD on stays at 0.8 volts. And so what happens there is that we have a new I sub x. So I sub x prime is 3.1 volts minus 2.4 volts over 100 ohm. So basically we end up with 7. We had 6 milliamps before for I sub x. I sub x prime ends up being 7 milliamps. Okay. Now let's, and so that was our starting point. So now, iteration 2, we're going to plug in this new number, plug in I sub x prime to get new VD on. Okay, so we basically get, now we got, again, we have this equation that I sub x prime is, we got the I sub s, we didn't change out our diodes from part A, so the I sub s remains the same as this guy, 2.6 times 10 to minus 16. And then we're sort of solving for, actually, let me use another equation that's actually easier, because we're solving for V sub D on. So VD on is V sub T natural log of I sub x prime over I sub s. Okay, so we have V sub T, we have I sub s, and we just calculated this new assumed Ix prime. And then, so VD on is 26 millivolts natural log of 7 milliamps over 2.6 times 10 times to the minus 16. And this ends up being, and then we have 3 of these. So V out is 3 times VD on, or V of this, let's call this V cell phone. And so this ends up being 2.4 2 volts. So it went from 2.4 volts to this. Okay, so now we run a third iteration. And so we plug this voltage in and find, what's Ix prime is 3.1 volt minus 2.412 volts over 100 ohms. That equals to 6.88 milliamps. So our first guess was 7 milliamps. When we iterate, it looks like it's 6.88 milliamps. And then we plug that in again for VD on. Ix prime over I sub s ends up being equal to 26 millivolts natural log of 6.88 milliamps over 2.6 times 10 to the minus 16 amps. That is equal to 2.411 volts. Okay, so iteration 3 is only 1 millivolt, 1 millivolt away from iteration 2. So we say, okay, we're done. So this is our solution basically. Okay, so if the adapter voltage changes by 100 millivolt, your cell phone voltage changes. So it went from 2.4 volts to something like 2.412. So your cell phone voltage changes by about 12 millivolts, 11, 12 millivolts. Okay, so let's see, delta V out is, let's say 11 millivolts. Okay, so this is what you'd normally have to do so this is sort of like the before picture of before using this small signal model. What you'd have to do is you'd end up calculating a starting point, which is this 2.4 volts. For 2.4 volts, we had a current of 6 milliamps. Okay, so that's our starting point. Then we said, we get a small change in the input voltage. So what's the new current and what's the new voltage? And we ended up having to take this iterative approach because we got a couple of things that are dependent on each other. And it turned out to be a little bit of a pain because we had natural logs and exponentials to deal with. Okay. And this doesn't look, it wasn't fun to do. And it took us a while, but it still didn't look so bad. It's doable, but you got to remember these are really simplified examples. If you added, a few more resistors, you added some transistors, we'll find out about later, and all that kind of stuff, it really gets unmanageable. So you kind of need something simpler, which is like the small signal model again. So basically in that case, this point would be your 0.8 volt initial assumption. And then you would quickly come up with this delta, and you'd be dealing with kind of a resistor type model as opposed to an exponential model. Okay, so let's see what this really looks like. Okay, so again, now we're proving, so this is sort of a proof, small signal. Proof is the wrong word. I want to just show you how do we get to small signal. Okay, so again, we have this V sub D, or is this I sub D characteristics? Okay, and so let's say initially we had this point V sub 0. That's where we started. And for that, we calculated I sub 0. We knew where that was. Okay. Now let's say we have a second point, and actually let me call this guy to be consistent with the book. I'm going to call this VD1 and this one ID1. And let's say now we have a VD2 leading the ID2. And the question is, can we come up with a simple way of calculating ID2 if we know this delta V? So we have this change in voltage. The question is, what is the change in current? And we want to, again, make this really a simple type of thing and not deal with exponentials. Okay, so let's see what happens. So, so what does this mean? Let's start with exponentials and figure out if mathematically we can simplify things. So if we had, so the ID1 is known, okay? So ID2 is I sub X, sorry, I sub S exponential of VD2 over V sub T. Okay, but VD2 is VD1 plus delta V. Okay, so this just equals to I sub S exponential of VD1 plus delta V over V sub T. Okay, so and then mathematically, this just equals, we can just rewrite this as I sub S exponential of VD1 over VT times exponential of delta V over V sub T. Okay, everybody with me right now? I'm just separating out the exponentials. Okay, so here comes the sleight of hand. And I don't know if you guys had heard about this or not. Have you guys heard about Taylor series expansion?
Yes.
Okay, great.
Yeah.
Long ago, but yeah.
So we're not going to go much into it, but let me just say, you know, if you have a Taylor series expansion of exponential of x is 1 plus x plus x squared plus x cubed, sort of an infinite series. Okay, that's a Taylor series expansion. Hopefully you'll find that in Wikipedia if you go there. So, and then what we're going to say is, okay, well, let's do a Taylor series expansion of this guy. So this guy is easy, right? This one we know, this first term is ID1, right? It's VD1 over VT I sub S exponential. So we have this one. So we're sort of out to simplify that term, okay? So let's say we do a Taylor series expansion of that term. Delta V over V sub T is equal to 1 plus delta V over V sub T plus delta V over V sub T squared plus Q, etc. Okay, so this is so just again Taylor series expansion. So now here comes this is so far so good. I haven't made any approximations or anything. Everything's good. And so here comes the approximation. So we're saying if if delta V is much smaller than V sub T. So remember, V sub T is 26 millivolts. Okay, so if this is the case, then delta V over V sub T squared is approximately equal to 0. Okay, so if this is a small number, you square it, you get even a smaller number. Okay, and then of course delta V over V sub T cubed is also equal to 0. So again, if just the number gets smaller, you cube it, then you to the 4th power, to the 5th power. So we're saying if this delta V over V sub T is small, so if delta V over V sub T is small, we're going to kill all these terms and all the terms to come. So then if this is the case, exponential of delta V over V sub T is approximately equal to 1 plus delta V over V sub T. So this is the approximation I'm making here. Okay, and so what I'm saying is, if this change, if this is, remember, this was delta, whoops, sorry guys. So remember, this is my delta V. This is my delta V. I'm saying if this change from VD1 to VD2, if this delta V is small or is much less than V sub T, and V sub C is 26 millivolts, okay, then I can make this approximation to this exponential.
So we would just have to check what the problem is specifying, how much we increase on the voltage or the current, and then we can kind of specify if we can use this or not.
Yep, exactly. Yeah. And another way to look at it is a lot of the circuits we'll look at, a lot of analog circuit design is designed so that you don't get these major changes, interestingly enough. So, and there's lots of reason, because you'll end up getting distortion, you'll end up getting major changes in your device characteristics if you have big changes in your input signals. And so they're designed that you don't get that distortion or various nonlinearities. But yeah, you'd have to check to make sure it's a small number.
Sir, can I ask you a question?
Sure.
So in your experience, most of the time you use small signal for like quick calculations?
Yes. So should I lie to you guys or should I tell you the truth?
Truth.
So,
Lie.
so okay. So there are. So let me put it to you this way. So depends on where you go in your career or your design. There's sort of two places. Let me just digress here. Kind of when you're doing electronic design for your career, you got two sort of paths. Either you're designing chips or integrated circuits, or you're building things on a board. Okay, so if you're doing stuff on a board, as we'll see later, you'll typically end up using bipolar transistors and diodes and stuff. And here is small signal. Yeah, use that a lot. So it's all about small signal. The reason for this is the supply voltages are large. Supply voltages are large. What's 1, too is bipolar transistors. I don't know. Sometimes it feels like God made them for analog design. I don't know. So they're good for analog design. Okay, so and by supply voltages being large, I mean they're like usually more.
Did he?
I think I lost him as well.
Yeah, he's
I
gone.
think you lost the internet or something.
Lost him.
Well, he's still here through his iPad, I think.
Hey guys, sorry, you guys lost me.
You're
Yes.
back.
Yeah, sorry guys. Let me do this. Live broadcasting and stop. Okay, God. I'm sorry guys. Let me. How are we doing on time? Let me just set myself up to go to. Should have done this. Got too optimistic. I think I lost my internet access. So let me go to my. I might lose you guys. I'm gonna go to my hotspot. Do I still have you guys? Hey guys, are you still there?
Yeah.
Okay. So then
Yes.
let me see if I probably lost my iPad, start broadcast. And come on. No? Boy, this is slow. Sorry guys, everything's terribly slow here. Let's see. Do I still have you guys? No?
Yes.
Yeah, you're right here.
Yes.
Gotcha. Yeah, I'm sorry guys. I gotta get out of the boondocks here and get good internet where I am. Okay. So sorry, I don't know where did I drop off? I was trying to explain how much small signal, how much large signal, but it ended up being the difference between designing integrated circuits or semiconductor chips, or designing boards. When you're designing boards, you're usually dealing with bipolar transistors, and you have larger voltages. Like you have your power supplies are 5 volts, 10 volts, 15 volts, something like that. And so all that really helps you to stay in the small signal model. So a small signal is really, I'd say it's, if you're doing designing boards, I think the small signal model, like you'd have to be kind of doing something wrong not to be able to use the small signal. That's maybe it's a good check on whether something bad's happened, like you peg some circuit or something. Okay. Do I still have you guys? Sorry, now I'm getting paranoid.
Yes.
Okay, great.
Yes, sir.
Okay. So on the other hand, if you're doing chip design, which is like something I do or used to do for a living, you use MOS transistors almost exclusively. And you also have really low supply voltages. So supply voltages we deal with are, I don't know, like you'd be lucky to have like a 3.3 volt supply, something like that. And then, so that's one. So your supply voltages are small, and two, MOS transistors were really, or at least, they were really like made for digital design. So they're really designed, or they were created and still mainly created, so you just sort of turn them on and off. And we take them and use them for analog design just for various reasons, and they just aren't as good as bipolar transistors with high voltage to do analog stuff. They're really good in doing digital design, but they're not so good in doing analog design. By the way, the reason you do that is because just for economics, right? So if you have let's say you have a product, you have a bunch of analog circuits, and you have your digital chip, right? Let's say you had a microprocessor that you bought, some from like Intel or something like that. There's a bill of materials, otherwise known as BOM. So these cost something, and this costs something else. And so overall cost is the sum of these two for your product. Okay. Now, let's say if you want to reduce your product cost, what you would do is you would put your analog circuits on the same chip as your digital circuits. And to first order, this is just about the same as your digital circuits, just because this is such usually from a area from the, you know, when you're designing chips, you pay for the chip area. And the area of these analog circuits isn't very big. So you end up basically paying the same thing for your digital circuit that has the analog stuff as you did for the digital circuit that didn't have the analog stuff. So overall, these systems end up being much cheaper than these systems. So people are constantly sticking analog circuits that don't really belong into digital chips to reduce cost, make this system simpler. Lots of good things happen when you do that, like your area of your board shrinks. You can go to lower supply. Power supplies means you can have fewer batteries, say, to use, and lots of good things happen. So this happens a lot when you start putting analog circuits into digital chips. If you're doing chip design, then small signal is just a good starting point, and it's just a starting point. Sorry, that was a really long answer, but
Thank you.
Sure. Okay, but again, I think the small signal is even in chip design that we do, it's still a good starting point, but you just can't stop there is the unfortunate fact. Okay, so let's come back to this. So again, the only thing I did was I did this Taylor series expansion of exponential, and then because if we just assume that delta V is smaller or much smaller than VT, then we can just stop at this first order term. Okay. So this was the key assumption. So now I'm going to stick this back into my equation. So I'm going to stick this back into here, and this is what we'll get. So I want to find out ID2 is I sub s exponential of VD1. I'm just plugging it in there, times 1 plus delta V over V sub t. I just plugged this into the exponential. Okay, so then I'm just going to work this thing. So I'm just going to multiply this out. VD1 over VT, so that's this one term, plus I sub s exponential of VD1 over VT times this delta. Let me move that guy over. Okay, so I just multiplied it. Then this is ID1 because this is VD1, and this is also ID1. Again, this is VD1. So this is equal to ID1 plus delta V, V sub t, ID1. Okay, so this is like this is sort of the key result here. So notice that When I changed my voltage, so when we changed the voltage by a small delta V, I went from ID1 to a new current ID2 that's related to ID1 linearly. I got rid of basically I just got rid of the exponential curve. Okay, so basically I end up, if the thing you know is we knew delta V, right? So we knew this delta V, that change, and we were looking for this delta I. Okay, instead of going through and calculating a new I sub D2 with exponentials and natural logs and things, we just have this really simple relationship is that the I sub delta I sub D is delta V I D1 over V sub T. Okay, so we just got, all I did was with this assumption that delta V is much smaller than V sub T, I got rid of the exponential. And now, I've got a much easier calculation ahead of me because all I have is this simple relationship, okay? So let me go around this explanation and write that again. So delta I sub D is I sub D1 over V sub T delta V. So it almost looks like I have, so what I did is, so I went from here to here, and it looks like just in this small area, just in this part of the curve, okay? Just in that part of the curve, I instead of having this natural log, this diode, I just have a resistor. And if it's as if my resistor, which I'm going to call R sub D, has a resistance of V sub T over I sub D1. Okay, just from this equation. This just looks like a resistor. Sort of a linear sort of linear dependence of I sub D, linear dependence of a current on a voltage resistor, and the proportionality constant is this ID1 over VT, which is like 1 over the resistance. Everybody see that?
Yes.
Okay. So what else would I want to say here? So, okay, so what happens is, so now some verbiage. This will stay with you guys forever. So there's, when you're doing like analog design, etc. So you talk about what's the bias point of your circuit. The other words for bias, it's not going to be on. I mean, well, just remember this for your future lives. There's some other names for this. There's also operating point. Some people call it quiescent point. But the idea is you put your circuit into some bias point. So that's your initial point. Okay. And then you have a small perturbation around your bias point. And that becomes your small signal. Okay, so you have bias point, and then you have a small signal around that bias point. And then this resistance for a diode, you'll end up with a resistance, you call this small signal resistance. Or incremental resistance. Okay. Okay, so let's do an example. Let's do a quick example. I think that's what the only thing we'll be left with here. So this is example, what the heck is, I think it's 3.18. In the book. And it's basically saying, well, a diode has we know it has a milliamp going through it. So this is our bias current. Okay. And question A is, what is delta I, or this change in current, if, so we have this sort of the V bias. Okay, we have that. And if V bias changes by 1 millivolt, what happens? How much change in current would you get? So once you give, I'll just give you guys a quick, like a couple of minutes to give that a shot. So I want to figure out delta I sub D. Okay, so let's look at, so from our equation here, this delta I sub D is equal to our first, our bias point current, which is I bias, over V sub T. V sub T is 26 millivolts at room temperature times delta V. So our bias is 1 milliamp. V sub T is 26 millivolts approximately, and delta V is 1 millivolt given by the problem. Okay, and so this ends up being 38.4 microamps. Okay, so again, instead of having to do sort of natural law calculations, etc., we just knew what our initial current was. We know V sub T, it's sort of like a constant given a temperature, and we can just use that and like sort of treat the whole thing like it's a resistor. And so let's see, how much more time do we have? Let me just finish with this, come back around with this idea that we have this diode, okay? And we basically are doing two things. We're saying it's a superposition of two things. A large signal, like a VD on, and we call this the bias. So this is in the voltage domain, okay? And a small signal resistance, R sub D. Okay, and this is equal to the bias current caused by this. So I'm going to call this I bias divided by V sub t. No, sorry. It is, I always get this wrong. So V is equal to IR. So R sub D is V sub T over I bias. So it's a superimposition of those two. So if you have a circuit and you want to use a small signal model, you have to use basically, let's say you had an input. Let's say you had a V bias plus, let's say you had a, sorry, so you had a input, a voltage, this is a capital V, and it had a small delta across it. Okay, and you want to see, basically want to solve this to see what this does. You basically treat this like two separate circuits. You put, let's say I have a resistor here. So I treat this like two circuits. One of them is just a diode, like a regular diode, but then I just used a large, this V1 value. Okay, then I might get large V out or large I sub 1 or whatever it is that I get. And I get the small signal, the small perturbation. I can, instead of using this diode model, I can just use a resistor model with this small signal resistance and get a small delta V out. Okay, and so V out in total is the large V out plus this small V out. You can basically superimpose those two values. And we'll see in the next few lectures how this is much easier to do the calculations than, again, using all the exponential and natural logs, etc. So, so anyway, that's where I'll stop now. Again, I wouldn't be surprised if you guys are a little bit confused, but as we go and do some examples, you'll see how what I'll try to show is that this methodology of superimposition of a large signal bias value with a small signal perturbation value is simpler, cleaner, etc., than doing a bunch of exponential calculations. Okay, guys, any questions?
No, thank you, Professor.
Okay, great. Thanks, guys.
Thank you.
Take care.
Thank you. Bye-bye. Take care.
Thanks. Bye.
Thank you.